Hello, and welcome to the Data Practitioner Roundtable on real-time machine learning. I'm Jordan Volz, the head of field engineering at Continual, and I'm excited to discuss the topic of real-time machine learning with our panel today. We are joined by Mark Atkins, machine learning architect at Freeport-McMoRan, Nisha Muktewar, machine learning engineer at SafeGraph, and Tully Merle, CEO and co-founder at Shaped. I'd like to thank everybody on our panel for taking the time to participate today and for sharing their knowledge with us. Note that everybody who is participating today is doing so on their own free will and representing their own viewpoints and not that of their employer. If you have any questions at any time during the discussion, please feel free to create a question in Zoom, and we'll leave some time at the end to answer any questions that may pop up during the discussion. All right, so let's jump in. I thought we'd get started with a quick round of introductions. So let's go around the table. If everybody could tell us a little bit about what they do at their company and how you got started in machine learning, I think that'd be great. Why don't we start with you, Mark?
Yeah, thanks. My name is Mark Atkins. I'm the ML architect at Freeport-McMoRan, which is a copper producer. We are the largest producer of copper in North America. So my role is centered around our internal ML platform and supporting data science and machine learning teams, a number of applications, including video analytics, predictive maintenance, and optimization and recommender systems for copper production. I got into data science and machine learning a little while back. My background is actually in nuclear engineering on submarines, but after I was done doing that in the Navy, went back to school, got a master's, started at Deloitte, and then ended up at Freeport, where I've been doing ML work ever since.
Awesome, thanks. Nisha, let's go over to you.
Yeah, sure. Hey, hi there. I'm Nisha Muktewar. I work as an ML engineer at a startup called SafeGraph. And what we do is we are building a global places data set that includes points of interest, spatial hierarchy, metadata, and things like spend at those point of interest and such. So specifically, I've been part of the spend product, so a lot of NLP related work. How did I get into data science ML? So it was like back in around 2005-ish, 6 timeframe when I started as an analyst at Deloitte's actuarial and modeling team. We used to build statistical models for insurance and retail companies to help them price their products or segment their risk. And that's how I got started crafting these predictive variables using tools like SAS and R, and then moved on to Python, Spark, etc. when I moved to Cloudera.
Great. So we have 2 Deloitte alumni on the panel today, which is, I think, a notable distinction. Tully, let's go over to you for the last introduction.
Great. Thanks a lot, Jordan. Hey, guys. Yeah, I'm Tully Merle. I'm the CEO and founder of Shaped. At Shaped, we basically build APIs for ranking and recommendation and mostly help out like content platforms and marketplaces increase engagement and generally build better experiences for their end users. Before Shaped, I was actually at Meta for about 5 years, worked on a lot of different AI teams there, worked in Facebook AI research, kind of publishing papers and more on the research side, and then ended up building PyTorch video and building some of the video understanding models for the production workflows. But how I got into AI, I think really just always was passionate about it during university, and then like while I Meta, kind of focused on that and worked on all of these different teams, and it's always been like a big passion of mine, and it's also why like I think started Shape to really help these smaller companies get this state-of-the-art research and AI techniques in their hands.
Great. And, Meta is doing a lot of really cutting edge work in machine learning. So I think that's a great place to cut your teeth for sure. So let's start this discussion by asking a really hard question. Everybody on the panel has been doing machine learning for years and years and years. I think most of you have been doing it for a decade, if not longer. If we can try to summarize your experience, particularly within the context of working in the real-time arena, what do you think is the hardest part of doing real-time machine learning? And let's go to Mark again for the first response.
Yeah, sure. So I think I'll work out the assumption that you're building something from scratch. We'll talk about that decision later, I think. But I think the hardest part is actually figuring out that you have a use case for real time and then designing an actual system to support it. So like I think doing batch processes is relatively simpler, and you can get away with having less than stellar or not a perfectly designed system. But when you go start down like the real-time road, lots of moving parts, lots of things that can break, lots of dependencies. There's many open source solutions out there for different pieces of those systems, but all kind of different opinions and different designs, and that makes bringing it all together somewhat difficult. So you have to have a team of engineers to fill in those gaps and form those opinions, and get that off the ground past whatever those open source options are.
Yeah, great. Nisha, same question to you. What's the hardest part of real-time machine learning?
Yeah, so I agree with Mark that real-time ML is an architecture exercise even before it is an ML exercise. I think that's what he was trying to say, and here's why. From a DSML, like a purely modeler perspective, right? Let's say you are building a recommendation system. The data scientist on the team or the model on the team basically builds a POC using some fancy ensemble models, maybe even employing things like embeddings and such to come up with recommendations for the user. So when it is an offline system, for most part, you train your models offline, do inference offline. So you can use, systems like in these, for these systems, basically, you could use tools like, S3 to store your data, and then use Spark to compute the features and save them in SQL tables or Hive tables, and maybe have nightly runs to do the inference, and then have the updated recommendations every day. But when it comes to near real-time systems, we need to ingest the data through Apache Kafka or Flink, followed by some aggregations or using streaming SQL engine, and store this pre-processed data in an online database. And so these online databases are typically low latency, NoSQL databases like Cassandra or Redis and such. And the reason why we need to do this is because for a model that's deployed in production, it is kind of hard to access data that is stored in S3 or HDFS. So we need a way of looking up these features, plus computing features in a performant way in an online database is even more difficult. So going back to the recommendations use case, as a GSML person, we really need to think what features can be pre-computed beforehand and stored in this online database, and what can be computed near real time, given the limitations of our, the near real time system that we want to design, and, thus the trade-offs that we need to think of when we try and design the system. So yeah. So I think that's why as a modeler, maybe you need to understand all these things. It will just help you build a better system.
Yeah, definitely. I'd be interested to hear your response to that, Toli, as someone who is or has been working with recommendation systems for a long time. Does that resonate with you? And also, what's your response to this question of like, what's the hardest part of real-time ML?
Yeah, no, it definitely resonates, and I agree with actually everything that you guys said. I think it's also worth saying, like, why is it actually harder? And it's because, like, compared to like a batch system, it really is like batch is really just a specialization of the streaming side, and like it's almost objectively simpler because of that. But in terms of what specifically resonated most, I think probably in terms of the feature computation, that's where I've always sort of seen like in all my experience, like always where the problems are, like whether it's like, the time and the compute that you need to actually do this computation, like, setting up Flink, like even the deployment of Flink and then actually using Flink or some kind of stateful stream processing is always difficult. And then also like managing like the point in time correctness between like joins with the offline features and like this kind of merging between what you've actually have offline and online. And I think, because you're getting into like the times and the orders that things are coming into and these like more like objectively more complex ways of doing joins, I think that's at least like, if I was going to say like what is the hardest thing, like that is the like one point that is just like consistent across every ML real-time system I've seen.
Yeah, for sure. So I think to summarize here, we heard system architecture is something you got to think about up front. You obviously can't deploy a real-time system if you can't support it. Handling features, doing computes in real time, handling latency, essentially a lot of things around implementing and maintaining a feature store are there. If you had a feature store
Yeah.
technology, I think that would help a lot with that process. And in my mind, a lot of those things are kind of like the first obstacles you're going to experience as you get into this real-time use case. I'm curious, though, like, are they necessarily the hardest parts of it? One thing that I often hear from people as I'm discussing real-time use cases as being super challenging is actually like after you get past all these initial obstacles, like monitoring your models and understanding, like, are your models doing well? Do we need to update the models? Are they giving good predictions? This whole piece around monitoring the models can be very challenging. So I'd love to get your take on that. Is this actually true? Are these things as hard? Are they not as hard? Nisha, do you want to take a pass at this?
Yeah, sure. So monitoring models, yes, but even before that, defining what metrics are you going to look at, where to capture them is an essential part to this, not only to just real time, but also batch workflows, actually. So metrics on training data versus real world data are quite different. We need to track metrics so we understand whether it is a covariate shift. That means, in the actual data, or like the features in the data, or is it like a real concept drift that affects the model performance in real time? And when this happens, this typically requires basically a lot of feedback loops and monitoring tools. And one thing, we need to think in mind is as we begin to scale from a data or model perspective, then it becomes an infrastructure problem again. And we need to invest in the right tools to make this manageable in terms of visualizations and dashboards or alerting mechanisms, that follow. So that's what I think is, again, more essential.
So monitoring gets back to system
Yeah.
problems again.
Yeah.
Mark, what's your answer to this question?
Yeah, like my short one is like model monitoring is hard, and like it's hard just modeling like a simple regression model. But like if we're talking like like a real time recommender system that could be based on an ensemble of models, like kind of something Nisha said also, like the metric's super important. Like sometimes your model accuracy like doesn't really matter. It does, but like I think of a scenario, something I worked on where you have a super accurate model that provides a recommendation, but if that recommendation isn't accepted or isn't used or drives the user down the wrong path, then your accurate model is driving zero business value. So something that's like attractive because it's accurate isn't actually valuable. And so monitoring that's really hard. And then tying that to underlying metrics becomes even harder. So I think there's tools out there. There's, you can throw a rock and hit an open source, monitoring or drift detection type tool, but tying that to your business use case becomes really difficult. So like tying all those things, your underlying data and, summary statistics of that data with your model accuracy with your business outcome needs to all kind of be present on top of, your Grafana, Prometheus systems monitoring to make sure your stuff's actually working. And it's hard to like pull that off the shelf or at a GitHub for a specific business use case. And so like again, it becomes a design problem once again. Seems to be a common theme already of this session.
Yeah. Well, actually, one thing, I wanted to add on to that is like, I think one of the big problems with ML monitoring is like, we're still back, we're kind of trying to coerce a lot of standard software engineering monitoring solutions into the ML modeling kind of paradigm. And I think that like even Prometheus and Grafana, they're not like totally designed for some of the specific use cases around like modeling metrics, and then how do you even compute these metrics just before doing that. And like, I think that's actually an area where like infrastructure wise, the solutions out there have kind of, at least the ones that I've seen, have like fallen short a bit. I know we've actually recently been looking a lot more into this at Shaped and just like looking at different vendors, and it's just tricky to work out how to solve it all nicely. And yeah, I guess I'm excited to see how that gets developed over the next few years through the open source community or other companies and whatnot. And I guess maybe one other thing to add on to that is like, almost this stuff needs to be thought of right at the start. Maybe this is really just adding on to the other stuff, but like almost from day one, because it comes into like, particularly if you want to do like multi-arm band A/B testing, kind of like reinforcement learning methods where you need these like almost like real-time reward of the system being fed back through. It almost like now you're actually modeling and results actually are the same as your like monitoring from a real-time kind of streaming perspective, at least. So from day one, you really should be focusing on this, I think. Almost, yeah.
Yeah, good point. I really like Mark's point in there about the fact, I think if I can summarize it, I think you basically had said the thing your business cares about may not be the thing that is easy to monitor in your infrastructure. So you may be able to monitor, like, I made a recommendation, did they click on the link or whatever, which, like, from a machine learning standpoint, you'd say, like, all right, my model's good, like I gave them the thing and they clicked it, and so, like, that was a success, that's a win. And those things are usually not terribly complicated to, like, feedback into your loop to get, like, a very quick monitoring validation on, like, did this prediction pan out or not. But it's actually a lot harder to, like, tie that into a business objective, which may be like, what's our daily revenue, which is something you're not going to know at that point. So there's, like, this lag effect that happens, and you're going to have to, like, go and, like, that's something the model probably doesn't even have access to at, like, the point that it's making the predictions. So you then have to go back and, like, figure out how you're doing all that. And I think a lot of these patterns are just not very well established out there in the ML ecosystem in general. But I think that's a great point, that, like, your business objectives and your ML objectives are not necessarily aligned 100%, and that can create a lot of complications in this. All right, next question. I'm going to go to Toli with this one first. I think when a lot of people start getting into real time, they kind of assume that real-time architectures have to be streaming. Is this correct? Is this something that, like, if I'm starting a company and I think I need to do like a real-time use case, do I have to solve, like, my general data streaming infrastructure first? Or are there different ways that we can do real-time machine learning?
Yeah, actually, this is something that's, like, definitely worth clarifying. Like, when we say real-time machine learning, what does it actually mean? I think, like, at least the way I think about it, there's like, obviously, real-time inference, which is the model actually being computed at real time. There's actually real-time injection, which might be streamed through, say, some Kafka streams into some online pooled when you actually do this online inference. And then there's actually also, like, online training. Like, I know TikTok came out with a paper recently about saying how they have this, like, online training scheme where you train every few minutes or something. And so, like, it's interesting when you talk about real-time AI, like, I guess I think about it in those three categories. To your actual question, I think that, yeah, like, doing the real-time prediction at this point is, like, the easiest of the three. It's kind of like deploy a model, make sure it's is efficient enough to handle the real-time use case, and then just, it's just a simple API, you can kind of feed it, and things are fairly like, stateless, I guess, right? That's kind of why it's simple. But then when you get into, like, this ingestion of real-time data, which then is, like, now feeding into this feature store, which now needs to be, like, aligned with your offline features and transformed correctly, and be ready, like, I guess, like, be available for when the real-time prediction wants to actually retrieve it. I think that's when things get quite tricky, and it kind of goes into this being, like, a real infrastructure problem of, like, now there's just so many more components rather than just, like, one deployed model. And so there's basically a big difference, and I think every use case is kind of different. Like, you can kind of start with just doing the predicted model, and then you kind of pass in some information through directly to the endpoint, and then I feel like you can kind of migrate over to the streaming solution and get more data in, and then get the advantages of this feature store and, like, hosting all the data. But in the end, yeah, it kind of goes back to whatever your use case is. You can ideally do the simplest thing, and I think also for the third one, the continuous training, like, I would say the majority, 99% of use cases don't need that, like, real-time continuous training. And really, realistically, there's only, like, few companies in the world that probably actually do that. But it'll be interesting to see how that develops as well over the next decade, actually. Like, that'll be the same thing.
Yeah, there's probably not a lot of companies doing continuous learning well, is my guess. There's
Right.
might be more who are trying to do it.
That's true.
All right, Mark, same question to you.
Yeah, well, I think one thing to hit on, that distinction between, like, real-time inference, ingestion, and training is interesting, because each one of those things, like, while related, they're kind of wildly different. And, like, to do one, you don't need to do the other two, but you may have desire to, add real-time ingestion on top of your real-time inference service. And that's just, lots of tech debt and challenges to, like, overcome as you rebuild. I think what's interesting too is, like, we talk about real-time, I'll say real-time inference for the next 2 minutes when I say real-time, is that, like, we're often, like, referring to, like, an endpoint or an API, to serve a model. which is great up until like you really need like when you have latency and throughput concerns, or like something on like an edge device. I think of some of the mining applications we have where you need to have something happening in real time out on the edge, and it's less ideal to have to hit an endpoint to get an inference. So then you also start thinking about, okay, well, how do I actually serve this? Is it as an endpoint, or do I need to embed the model in the application? Lots of trade-offs there. I mean, it becomes harder to update, refresh, do things like that with an embedded model, because it requires basically redeploying your entire application. But it can also give you, benefits if throughput or latency are super important to you. It's again a cost benefit and a design decision that needs to be made early, because it wildly changes how you design a system.
Yeah, that's a good point. And I do think that if you go out and read the ML literature, most of it, I'd say like probably 90% or more, is geared towards the real-time inference via model API endpoints, where whatever is a prediction has internet connectivity and can do that, and you're willing to eat latency that could be as high as like a second or two in getting that response back. But I think you're entirely correct. There's a lot of use cases that you could envision where a second latency is not really valid. Like, I want sub 100 millisecond latency on this prediction. Like, how do we do that? And in that scenario, you're now really getting into like embedding it, or you could be in the Internet of Things category, where it's possible you may not have internet connectivity, but you still need to make a recommendation or prediction or something. Those use cases definitely exist. So good thoughts there. I do want to ask a question here that I think could be potentially controversial. I'm interested to get everybody's take on it. Nisha, I think I'll throw this to you first. I think, so much of machine learning and data science is done within the Python ecosystem. And when we're talking about latency and things being fast, you often hear that Python's a lot slower than things like C and Java and Go. So is Python really even the right language to be working within if we're doing real-time machine learning, or should we be exploring other ways of accomplishing these things?
Are there others? That's the question. So most of the dev work these days, at the moment, at least as far as I'm familiar, is being done in Python, especially if you're focused on employing the latest and the greatest ML techniques or using some libraries. So the ML community is generally focused on that. That said, given the real-time system and how fast things should be, I've seen that, like, as for me as well, I kind of often do development work in Python and then rewrite in Scala for production. There are also situations where part of the workflow is in Python and rest is in Scala, depending on what the use case is. It's kind of totally dropped Python because, most of the data scientists, and I also came in from a very similar background. We are not so well versed in software engineering practices, which are kind of critical for these faster languages. And after all, for a typical DS person, it could be just means to an end, and we are more focused on solving other problems, basically, versus the software engineering ones. And then the other part of it is like dependency management in Python can be a pain, and other languages seem like they do it better. You just basically build a jar and put it out there, versus all dealing with all the pain points of different libraries trying to come and work together. Yeah.
Totally. I'd be interested in your take. I think if I recall correctly, Facebook is very heavy on C use. So I'd be curious of like, what was your experience in that? And like, is Python the go-to production language, or are they trying to do more stuff in like C and Java and stuff?
Yeah, so I guess at Facebook, the way it kind of worked is mostly like data scientists or ML engineers would be creating like PyTorch models. And then you have to just make sure that you can like implement it in Torch script. So then it's going to compile down to something that actually works in like C++, and then it can be kind of integrated in the production pipeline. And I think this kind of process works well, where you actually, for them, like your model definitions and things are mostly actually being written in Python still. but then you have this kind of like compilation process down from Python into something that's actually hardware accelerated. And it actually goes into my general like thoughts around this is that I basically think totally perfect, like fine for the job for inference. And nearly always the low-hanging fruit is optimizing like around, like you use Python as your high level like logic to go through even through inference or whatever the critical system is. And then you go like, okay, you know, let's actually use NumPy, which is essentially backed by C to do some actual operations under the hood. But like as a practitioner, you're not actually the one implementing that. And then that's also, there's like, I think that's a great thing about Python is you have a lot of optionality about like starting with something like a general Python kind of program that's easy to use, then decide if you want to use a different package that is backed by C externally, or like, for example, at Shaped, we actually recently found that like we couldn't implement like a Bloom filter for the recommendations in Python. It was just like no way to get it speedy enough. So we just built a Go, you know, Bloom filter package and then can just integrate that in and now like the problem solved. So I think it's like, you want to start with Python. It's a good workflow and that's like no problems there, but you just have to you want to be ready to re-implement the things that are actually causing issues in the language you want, but doesn't mean, you know, it's not just like a 0 or 1 replacing, which I think is maybe what some people, or at least like there's a lot more like nuance around the question if you think about it that way. And that's, I think, the important consideration.
Yeah, so ideally we have an interoperable framework where we can write in one language and compile and run it
exactly
in another language. Yeah.
Mark,
I'd love to get your take on this as well.
Yeah, I agree with what everyone said so far. I mean, I think like objectively Python is slow, right? Like if you benchmark it next to C or Rust or Go, like it's slow, but writing Python code is super fast. And to Nisha's point, like most of our, you know, the data science community writes in Python or R, is familiar with it. So like it, you know, I think the argument that like you should stop using Python is silly. I think there's some interesting, like, you know, Python 3.11 and, you know, the reworked C backend is super interesting. I think there's some really cool things like, you know, Google BigQuery or Snowpark that are allowing people to interact, you know, in a Pythonic way, but taking advantage of, you know, faster operations. And I also think like, you know, the PyTorch thing Tony was talking about with Meta, same thing just like TensorFlow, you know, I think there's a Rust crate for TensorFlow, there's a Go implementation. A world where that was a little more standardized would be cool. Like, you know, think of like, I don't know, a tarball or a zip file, like a world where there's like some like standard for model serialization that you could then, you know, drag and drop and use in different languages or frameworks would be awesome, because like there's definitely a need or a use case to have faster inference or faster processing times that Python can't support. But like our ecosystem will always be, will be for a long time, I think, you know, Python centric. So finding, you know, ways to allow other frameworks, languages to play nicely is critical. And I'd love to see a world where it's super easy to do those things. I mean, you know, there's great reading and people doing cool work online, but like there's no standard, there's no, you know, it's still a maturing space. So hopefully, as we all grow, it'll kind of come to a head and we'll have like, I don't know, equivalent standards for machine learning that we have in the rest of the engineering world.
Yeah, that makes a lot of sense. So I think something that we've kind of been hitting upon a lot in all of our answers here is just that system design and kind of like architecture is very important in a lot of these real-time use cases. I think when I talk to people out there in the data science community, you definitely come across a lot of like notebook slinging data scientists who are writing in Python and R. And I think like they're, what they're focused on mainly is like use case solving, right? So like the business gives them a problem, they come up with a model and like maybe a data pipeline that solves that problem. Usually they're not, you're not responsible for production. So I think a lot of companies have started spinning up machine learning engineers who are a little bit more focused on actually building out the full production system. But then I think like our discussion today kind of indicates that like the types of things you need to know for real-time systems about like, writing in C, and like maybe you need to know about Flink and Kafka and streaming. Like, I think a lot of these are perhaps outside what I would typically anticipate a machine learning engineer would be strong in. So I guess my question here is, do we think that there's maybe a need, like if you're a company who wants to do a lot of real-time machine learning, do we need to like kind of think about like a machine learning architect role? And this role is focused more on like architecting the the entire system, which then like data scientists and machine learning engineers would come in and like instill different pieces of the puzzle, but they would kind of be in control of the overall architecture. And I guess, Mark, maybe you're a good person to answer this first, as you are a ML architect, at least in job title. So I'd love to get your take on this first.
Yeah, I'm definitely all for the role existing, since it is my employment currently. But like, I think what's interesting too is like the different definitions. Like you kind of said, like, you know, in title of ML architect, like what does that mean? Like I don't know. I mean, I do a lot more dev work than I do architectural work. Like I write way more code than I do, making Miro diagrams. But I think the same is true of like data scientists and ML engineers. Like if you look at a job description for any number of companies, the definition of what is an ML engineer is like wildly different almost everywhere you look. No one actually knows what it means. I think the role of a data scientist or data analyst has become a little more solidified, but ML engineer could be anything from like a data scientist who like has a more end-to-end knowledge of things to like a software engineer who's supporting machine learning, and like everywhere in between. So that being said, like I think it's important for companies to understand internally what their team and platform need to look like instead of necessarily hunting for job titles. Understanding the capabilities you need and filling those with people. Whether you call them ML engineers or architects or I don't know, pick any random name. It doesn't matter as much as like understanding your use case and goals and finding the right people. So like if you call me an engineer or an architect, like it doesn't really matter as long as like I'm meeting the needs for my company. But then you have to like figure out what those needs are so you can make JDs that actually attract candidates. So that's a whole different discussion. But like
Yeah. Nisha or Toli, do you have a response to that?
Sure, yeah, that's such a great answer and a response by Mark, by the way. And so I totally agree with the titles and all that. Basically, all that you need, like, as far as I understand this, is someone who has some DSML background, who has built ML systems. And by that, I mean, they have some ML background and built models and so on. They also need to have, at the same time, a better understanding of things on the DevOps or platform side of things, operationalizing end-to-end ML pipeline. So especially if all these things can come together, then, whoever that person is can be an ML architect. Yeah.
Yeah. One thing I'll say is like, it's a good question. I agree that the titles don't matter as much as actually the skill sets between these, like, are you more data scientist? Are you more backend or ML ops? And actually going into like, why is real-time AI hard? Like the first question, potentially it's honestly just hiring people that know the cross of these things. And I think that's like, there's a big mismatch between the personas that have come from like maybe core data, like backend and like data science and things. And you really need some mix of these things to like build the right solution and actually do the, I guess, be an architect. And so maybe that's where, I think this is the right mix between these two ends of the spectrum is tricky and important here.
It also like begs the question of, for many of these things, like this is a decision you made even beforehand, like, do we want to build out a team to do this, or should we buy a platform, off the shelf? Because like everything we've talked about, like, there's a lot that goes into this, but there's also like an even earlier decision, like, are we going to be a company that builds everything from scratch internally, or do we focus our effort on just the models or just one specific use case, pay someone else to give us the infrastructure, and then don't worry about everything else. I think there's always trade-offs to both those things, but it's more relevant than ever.
Do you think that so a question for you, Mark, follow up on that. When you go out there and you look at existing tooling, so I mean, if you do say we're going to build it from scratch, the reality of that is probably like we're going to go use a lot of open source stuff and not like build everything from like scratch itself. Do you think that, and I think in your first response about why is ML hard, you had alluded to like there's a lot of complexity in the open source arena for this. Do you think that like in the open source community for machine learning, is there enough tooling that's like purpose built for real-time use cases? Do you have enough things that you've like, if we want to build it from scratch, like we can go, get a real-time or get like an open source feature store, get like an open source API deployment platform. Is that like feasible? Is it feasible but really hard, and you still have to end up hiring a lot of these expert people who have done it before? Or is it just that like these things are too early, they're not thinking about the right things like security and all this other stuff? We have to spend too much time integrating it. You may as well just build it from scratch. What's your take on that as somebody who's probably been doing this for quite a while?
Yeah, I think a lot of it comes down to like how many people or how many dollars you want to throw at the problem, because that's what it ends up coming down to. Like, first of all, like even if you say I need to build it from scratch and I want to, but I can only hire one engineer, then it's probably not the right answer still. I think, the major cloud providers come close to everything in like a very generalized sense. And so, companies typically start there. If you're an Azure shop, you start with Azure ML or Databricks. If you're an Amazon shop, you start with SageMaker. And then, you might find that gets you all the way there and it gives you everything you need, within the bounds of those platforms' opinions, or maybe not. So then you start searching for kind of like, the next tier, whether it's open source or, or not, like, the Tecton Feast type of discussion. Like, well, Feast is here, it's open source, but it's like still not like trivial to implement, even though, it's open source, but like I can get almost the same thing and pay money for it, and have, all the support and engineering that entails. So yeah, like, I mean, my Deloitte consulting answer is it depends. But I haven't gotten to throw that one in there yet. But like, yeah, it's tough to decide. But like, I think it really boils down to like, how much do you want to throw at the problem monetarily in terms of like, resource devotion? Because if it's not like, if the answer isn't somewhere near like a lot, then you should start looking, at I think either buying or really, greedily harvesting open source tools and focusing on linking them together instead of building things like, your own internal ML flow from scratch.
Right. Nisha or Tully, do you have a response to that? All right. Sounds like you don't. That's just fine. Question, and then we'll go to the audience question. So if anybody in the audience has a question for the panel, please submit it over Zoom, and we'll start answering them after this last question. So my question is, and I asked this on all of our data practitioner roundtables, what is it something you think people don't think enough about as they start building out their machine learning systems? Or another way to look at this, like if you go back in time and tell yourself like one piece of advice at the start of your career, like what is a really good piece of advice you would give to yourself? So we can start again with Mark on this one.
You can put in the spot. I think my answer will sound cynical, but it's not intended to be. Like I found through my progression that like I used to be very, very model centric, thinking that like model building was like the end all be all of this line of work. And I'm at a point in my career now where I think models are kind of uninteresting and everything surrounding them is what's interesting. Now, like that's not to say like it's still like the main business value driver in any ML solution, like you need an ML model, like that's goes without saying. But to me, like the hard part has always been the surrounding infrastructure and building the tools like to get those models somewhere useful. And so I wish I'd gone down that path earlier rather than later, because for many like I don't know, probably 80% of use cases out there that someone's built a model very close to what you want, and it's probably out there on Kaggle or GitHub, and you can start from there and have a pretty good, almost good enough answer. But it's a lot harder to build your system around that. So I wish I'd spent more time on the infrastructure and less on the model. I mean, that's my whole life now, but you always wish you'd start something sooner, right?
Yeah, exactly. Nisha, how about you?
Yeah, very similar, I would say. So again, spend more time learning engineering, tooling around it. So, back in the day, like I mentioned earlier, I started with R, SAS, and then Python and so on. So didn't really think of software engineering tooling in this space. But as you build ML solutions, you realize that scale is important on all fronts, be it data and, other areas too. So getting familiar with software engineering way of doing things can help you grow tremendously. The other thing I would say is paying more attention to what is going on in the industry, because it kind of changes quickly in this space. Yeah.
Yeah. And totally, how about you? What's your piece of advice?
Yeah, I mean, for the question of like starting a new ML project, things to focus on, or like at the start, I've always thought when you build these ML systems, like a lot of people would just think like you're building it for the end result and like the outcome and what you're predicting. You're actually building two things. You're building an interface for your to do experimentation, and then you're doing also the output result. And I think sometimes people forget about like the building for the experimentation workflow, and like that it's actually very like the iteration speed that you can do experiments is like just as important as the actual how fast your inference speed is or something like that. And because it actually will allow you to get good results. And it almost goes into like, that's why the model monitoring is almost like, you should think about that from day one, because that's actually how you are going to be able to experiment. In terms of the more general question of like advice I'd give people getting into it or like things I wish I would know, I would know earlier is I've always thought people either come from like people getting into ML engineering either come from the like math statistics backgrounds and then learn the engineering skills and then basically like piecing that together, and then now they're an ML engineer, or they're like a back-end and like general software engineer and they've learned like the math and statistics and now they're an ML engineer. I think it's worth understanding like where you are, which pathway you're going for, and then really focusing on the other side. I think like for me, it was, I wish I had focused on like way more applied mathematics because I thought it was really hard to learn that by yourself outside of university. But then someone from the other side probably would kind of explain the other way around learning the software engineering tools. So that's one bit of advice: be cognitive and trying to balance those two areas of learning well.
Yeah, that's good advice. And I think you're right that it's probably more difficult to teach yourself advanced mathematics online. I think there's probably larger, more resources online for learning software development than, or at least like the level of software development you can need as a data scientist. Like you can get by without being like a complete expert usually.
Yeah.
All right, so going over to the questions, we have a question here from Gus, which I think is a very good follow-up to that question. He says, software design and software engineering best practices have been big themes of the responses so far. It would help me tremendously to know how the panel might define design/architecture and software engineering best practices for machine learning. Anybody want to take that?
Yeah, I guess like when I think about architecture design and software engineering and like almost like going to the last question of these two areas, I think of it as like essentially like a back-end engineer or distributed engineering or like data engineering as like one kind of persona where it is almost like architectural, like think architectural diagrams of how data is being stored, how data is being ingested, streamed, read write between the stores, and then also the scale of all that data, like how does like actually looking into the number of bits going through each of these and designing smoothly. So in terms of, that's like how I define it, by the way. In terms of best practices, I don't actually have a specific answer. Maybe I'll hand that to one of the other panelists. It's so general a question, I think.
No, it is like my super broad answer is like, when I'm starting a new project, I do like try to start with like a cookie cutter or the bones of like a Python application and not necessarily a notebook. I'm not a data scientist, obviously, but like, on some of our teams, we've built kind of the Python application, that can then be interacted with, from a notebook or from, an API first, and, written, all the underlying unit integration tests, CI/CD pipelines, that sort of thing, like to then allow a data scientist to use that, that framework to train and deploy models. That's kind of like a micro scale, like an ML platform. I'm thinking just like at a project scale, but like, doing things like that to start with, kind of ensure you have, you're writing an application, not just an interesting notebook. And starting from that point is much easier than like, an experience of like refactoring a giant notebook into a meaningful application. I've done both. I prefer option one, definitely to option two.
So, I'll also try to answer this question, especially recently, and what has worked for me since a year or more is basically that very first definition of the problem that you try and define. And, let's say you're predicting something or trying to do some kind of named entity recognition or recommendation or something. Start with something simple in ML. Define that problem clearly. Start very simple model, whatever that may be, or simple technique that you want to employ, and take that and don't think of doing everything in that notebook. Take that, but try to write almost close to production code, not exact production code, but close to it. Take that and go through the entire process up until where you are scoring your production data with your new technique or whatever that model is, and go through that entire process at once, one iteration. And if you can do that in one single go, then all you have to do is change this particular piece of model or whatever, and then iterate faster. So yeah, and that will help you. No definition of test data set is good enough, because the real test data is your prod data. So you better go through this cycle once and keep changing and iterating that faster. So it will help you build a better and come up with a better design and architecture of what you really want.
Yeah, I think failing fast is something that I always come back to in technology, which is like, if you can design your workflow to fail fast, you'll probably get to somewhere useful in a shorter amount of time. I love the idea, Mark, about the templates. And if I could answer Gus's question, which I'm going to, I would say, like, when I think about, as I talk to just a lot of different companies about over the past 10 years about the machine learning processes, I think a large obstacle that companies have is data scientists are typically notebook oriented. They really don't follow any kind of like software process. So their end product is kind of like, I can run this notebook and I get like some kind of an answer to your business problem. And then they'll throw it over the fence to someone like Mark or Nisha or Tully and be like, you're the machine learning engineer, make this work in production. And you're like, wow, this is just a hodgepodge of crazy notebook nonsense. Like, I'm going to spend forever trying to figure out what's going on. And you may have to rewrite it in Scala or Java or C even, but like, even if you don't have to, just like refactoring that code. Because like, as a software engineer, you want to do things like define classes and write modular functions and like be able to test those functions. And these are things that like data scientists are not thinking about. They're not thinking about like, hey, I probably shouldn't write my entire thing as like 200 lines of Python in one script, which is a software engineer. I remember my first job out of college was a software engineer. And I remember we were doing like onboarding and they're like, if you ever write more than 10 lines of code in a function, we are going to reject it and you need to go refactor it. And they were very big on like, a function cannot be more than 10 lines of code. That's a hard rule. You always have to write less than that. Like, you call something that you like refactor in a different function and call that. And I always come back to that as I see people's like notebooks and like, oh my gosh, like you would be failing all of these tests that, in my first job, we were subject to. So yeah, I do think, recently there's been more of a trend to getting into that software engineering best practice for data science. I think, data science a decade ago is very new, and now I think we've seen enough successes at places like Facebook and like other high-tech companies, and like those people have left and start to spread the gospel of like, hey, like, we should treat this more like software engineering. Not that they're necessarily exactly the same, but there's a lot of like really good things about software engineering that we can apply to our machine learning workflows that make them more robust and predictable. Right? Like, no one loves waking up Saturday morning to like failed production pipelines. That's no good. I have another question I thought about. Tully, you had said, I was going back to your idea of like, you've got your software engineering over here and you've got like your math stats over there. And if you go like the classic diagram for data science, I think you often see like math stats, computer skills, and then like business domain expertise or something. I've always thought a missing piece of that is just like data. And I think like the more I've worked on machine learning use cases, and I think it's particularly now since there's more of a push towards like making things operational, making like real production jobs. It means like your machine learning workflow inevitably uses data, which means you have to have a data pipeline in there, which means either your machine learning team has to understand how to create data pipelines, or you have to work with data engineers who do all of that. So I don't know, I guess like, I'm not sure what my question is here, but like, are we starting to add like too much to the pile that we expect people to know in order to like actually get a production machine learning job out and into production? Or is it just a matter of like, hey, if you want to do machine learning, it takes a lot of people, it takes a lot of like investment in terms of like resources and dollars to get that done?
Yeah, I think it's like it is, I don't think it's like putting too much things in there. It's just like a shift of the skills that people need to learn. And if you want to focus on this, like that's just part of the requirement. And I think also like you can always specialize in just one of them and not learn the others, and that's fine. Or if you're at like a startup, like you have to learn all of them, and like that's how it goes. And I think I generally think that's fine from a work, you know, how these things are built. I do think because the solutions, like almost like the infrastructure solutions that abstract either of the skills of all of these is so immature. That's why you have to learn these, and like slowly, ideally, like you're cool, you're a data engineer without the data science experience. That's fine. Now there's like a whole lot of models that you can use, and that's actually no problem with Hugging Face. Or like maybe you're the data science and the like backend archetype, but like maybe there's a really good workflow management solution or something like Metaflow. And so I feel like we are slowly getting to this point where you have to learn less and less. But I think it's really just the same as what happened in software engineering, where like there was different kinds of specialty backend, front end, but it's like you kind of ideally kind of know them all. And depending on the team size, you can work out how much you want to specialize or not.
Yeah, that makes sense. Any other thoughts, Mark or Anish, on that?
No, I totally nailed it. I mean, like, it's impossible to like, I think it is impossible to like be an expert at every single thing, you know, like whether it's data science models, machine learning, software engineering, like no one can do all of those things and be like a one man or woman show. Like that won't happen. I do think it's important as you know, like the ML community grows and matures, like that people in different specialties have an appreciation for, you know, their peers. Like I should understand, you know, the data science persona and understand what that person needs to be successful. Just like that data science persona should also understand like what the engineering team needs to support them. And once you have that, you know, people with their specialties and doing the things they're good at can kind of work in this, you know, harmonious, you know, happy world where everyone's doing things they're good at, but it's all, you know, interconnected and working together. So the short answer is like it's important to like still understand the different parts, you know, of the problem you're trying to solve, even if you are super specialized. And there'll always be a need for that too.
Yeah, totally. Sorry, go ahead, Nisha. I didn't mean to.
No, I'm just agreeing with both of them. They just nailed it.
Okay.
So yeah.
All right, one more question also from Gus. I think this is probably going to be our last one unless short one comes in while we answer this one. Gus said, broad question. He's curious what the panelists are looking for 2023. If we came back in a year, how could this conversation change at all? You know, a year might not be enough time. Let's say like, you know, 1 year or like 5 years. Like in the next 5 years, how do we envision real-time AI perhaps being different?
I'm gonna like one of my answers. Like I'm hopeful that like they'll just be kind of a more generalized standard in our world for you know, things like a term as vague as models, or you know, or model objects, or just kind of different parts of our workflows. I think we have lots of different vocabulary that means different things, but you know, I long for a day when like, you know, we say Git, everyone knows like version control for software, where there's like some word that like everyone's like, oh yeah, that's the thing for models, and this is how you use it. I think like, you know, standardization at that level will be super interesting, and make my life a lot easier. So
yeah, I think even
I'm not gonna to hope for.
With the standardization, like I think a good example is even if you say feature store, like that could mean so many things today. And like I feel like I would like to think in 2 or 3 years, like there's a concrete abstraction around the feature store that's like fairly well defined that maybe doesn't need to be debated so much. And like, and I think, yeah, a good, that kind of follows probably from like a leading feature store provider or open source project, kind of like defining the whole category. And so excited to see that pop up for all of the different components around this stuff. Actually, and also I would just say like, if it's not real time and it's more just like standard AI, I think all the generative AI stuff's awesome, and I'm really excited to see what that is in 5 years. I think like a big thing I'm passionate about is that I think like these large language models are being applied to very verticalized things and only being used by just like kind of all people that know how to use machine learning and whatnot. But I think the abstraction's general enough that it could just become another tool in any software engineer's kind of workflow. And I think when you apply it to these like in between glue tasks between just normal software engineering as just like another tool, just like writing a Python function, there's going to be like a lot of exciting just value that comes out of that. But that's separate to the real time.
I would say, going back to Tully's question, like initial response, and are there enough use cases where there's real-time training and there's real-time prediction, near real-time prediction as well inference? Few years back, 6 years back, we asked the same question and it's still here, and maybe we'll see more in this space. And maybe it'll change our answers, responses. I know there are very few companies who do it, but yeah, maybe it's more standardized going forward. We'll see.
Yeah, I think a big blocker here, which hopefully 5 years out is different, but I think I actually would have said this 5 years ago, and it's still true, is that streaming is too difficult for most companies. And being at Cloudera 5 years ago and sitting in, and I had customers who were doing streaming, and it was just like, it was very challenging. They, the ones that were succeeding had like, tens of people working on it, which is not sustainable for like any but the largest companies out there. So I think like there's a disruption that will happen at some point in time in the streaming field that will just make streaming super easy, kind of the way that like Snowflake has made SQL in the cloud super easy, which has obviously been a big unlock for them. I think we'll see something in the streaming category as well. I think machine learning will then follow closely behind. Like once your streaming data pipelines become super easy, then I think it's more easy. It's easier for your data team and your machine learning teams to like think about their use cases when it's actually possible to execute them without like a crazy amount of effort, I would say.
Great.
All right, well, we are right up at time here, so I want to thank everybody. Mark, Nisha, Tully, thanks a lot for being part of this panel. Thought we had a great discussion. Thanks to the audience for attending and for all the questions, and we will catch everybody next time.
Thanks a lot.
Likewise, thanks.
Sure.
Okay.
Right.